Chapter 5 is all about eigenvalues and eigenvectors, and it really helps to see some examples of this rather than just trying to see a definition. However, let's take a look. The definition of an eigenvector, and this is really important, is some non-zero vector such that when I multiply the vector by a matrix, the result is just a scalar multiple of the vector. All right, so that's the important relationship, and we'll be looking at all of this. And when it happens, the eigenvalue, lambda there, the Greek letter lambda, is the eigenvalue. It's the scalar multiple. And the vector v is the eigenvector. And so they always come in pairs. These eigenvalues and eigenvectors come together. So just a quick note, eigenvalues can be zero, but eigenvectors can't. So by definition, eigenvectors are non-zero. But we do occasionally have a zero eigenvalue. And that will also turn out to be the case that whenever having a zero eigenvalue, the determinant of that matrix will also be zero. We'll talk about why that is. Now, this section of the book is extremely good at giving examples geometrically of what's going on. And here they just ask if you have v and w, right? If you have these two vectors, how can I tell whether or not they're eigenvectors? Well, I just multiply. Right, so I took the matrix V, which is 1, 1. I multiplied it by A, right? I transformed it using the associated matrix A for the transformation, and it turns out to be a scalar multiple of itself. Okay, but with W, notice that I can tell this is not a scalar multiple, because if it was, it would have to have the value of 3. So we know that V is an eigenvector, and W is not. Also, I know that the eigenvalue associated with V is 4, because that was the scalar multiple that popped up when I did the multiplication. Finally, before I do some examples, I will say that you should definitely take a look at the examples in the book. Several of them are interactive, and they show you what's going on here. So for example, here is going to be a reflection about this dotted line, which is the line y equals negative x. And when I'm doing this reflection, we can see the different eigenvalues and eigenvectors geometrically. So I like how they do this. And they even have a nice interactive chart here where we get to move these values around. And when I get onto this line, y equals negative x, you can see that a of x and x are landing together, right? And when I get onto the green line, they're landing in opposite directions. So when they're landing in opposite directions, that's an eigenvalue of -1. The eigenvector is pointing in the opposite direction. Or excuse me, the transformed vector is pointing in the opposite direction of the eigenvector. And so you should definitely take your time to go through these interactive examples and see geometrically what it means for one of these transformations to have eigenvalues. So I'll just go through an example here next. So in this example, the matrix S is a shear matrix. And all it means is that basically we just have the identity matrix with something additional going on. Well, this is going to take the x component and shift it to the right because it's a positive shear. But that's not so important. The geometry is covered in the Marguerite text. What we're going to do is just check and see whether or not V is an eigenvector. And all we have to do in this case is just multiply them. So I take S times V. Sorry, I didn't create V. So the next thing I need to do, V equals 1, 0. All right, now that should work. And you see that not only did S transform V into a scalar multiple of itself, the scalar multiple is 1, right? It didn't change the vector at all. So this corresponds to an eigenvalue of 1 and an eigenvector. This is an eigenvector. Okay, so that's all we have to do. Let's do some examples, but with larger matrices. So here we have the matrix B. And let me make this just a little bit larger. We have the matrix B. You can see, and the question are, which of these three vectors are eigenvectors of the matrix? Okay, well, we figure this out by multiplication. So let me just print out the vector V so we can see it. And then let's take B times V. And this one is very easy to see that no, there's no, it's not a linear multiple, right? Any scalar multiple would leave a 0 here, and we don't have one, and 2 times 3 is 6, and 1 times 67 is 6. Yeah, this is definitely not an eigenvector, right? It's got the wrong kind of properties. Let's take a look at the matrix U and multiply instead. Oops. And multiply here by the matrix U. And now this is interesting because we do, in fact, right, have an eigenvector. Look, this is 2, negative 1, 2, 4, negative 2, 4, right? So this eigenvector U corresponds to an eigenvalue of 2. Okay. Well, that's fairly easy. Let me also show you that we can do, once we know this, we can check and say BU equal to 2 times U, right? And what happens is I get a logical array. And if they're all ones, it means that yes, in fact, these vectors are equal. So this is another way to check if I know an eigenvalue eigenvector pair. I can just do the multiplication this way with the conditional, which will produce all ones if it is true, and at least 1, 0 if it is false. So that's another quick way to check. The final one we wanted to check was W, so let's print out the W vector and change the multiplication here. Well, let's look. Let's just leave it with a W and a W. And yes, it is. But why don't we look at what the multiplication turns out to be? Oh wait, I'm sorry, it wasn't. So this is what I was looking at. When I do this, notice that I got zeros, right? So let me just come back here and see what the eigenvalue is. I can see the eigenvalue must be positive 3, right? Positive 3 times the negative 2 will give me negative 6. Positive 3 times 1 will give me the 3. So I know that this corresponds to an eigenvalue of positive 3. Well, now I know what to do, right? With my conditional, I can go equal, equal 3 times W, boom. Then I'll get my all ones in my results array, my logical array. I know that that statement is true. Okay, so what did we determine? We determined that the final two, U and V, they were in fact these eigenvectors of the matrix B, and V was not. So the rest of this section is very much about the geometry, and again, you should go through the interactive examples. We have a theorem that says that as long as the eigenvectors are from eigenvalues that are distinct, then I know those vectors are linearly independent. So let's just say I had a 3 by 3 matrix, and every single one of its eigenvalues was distinct. Then I know that the set of its eigenvectors is linearly independent. And this also gives us some cool facts. For example, the most important one is the fact that there's a maximum of n eigenvalues. Why? Well, because I can't have more than n linearly independent vectors in a basis for Rn. So So we know that there can't ever be more than n eigenvalues. Now this is some of the most important algebra in all of mathematics, this right here. So let's just go through it because this is how we verify um, eigenvalues and eigenvectors. All right, so this is just the identity. This is the definition of an eigenvalue and an eigenvector. They are a pair of a scalar multiple eigenvalue and a vector, an eigenvector, non-zero vector eigenvector, such that A times the vector V is a scalar multiple of the vector V. Now, what's happening here? Well, here we're just subtracting the lambda V from both sides, and so this is the zero vector. And then they're multiplying by the identity. They're putting the identity in here. Why? Well, we need to factor. We're going to try to factor out a vector V. And again, this is the vector 0. It's not the value 0. So then we factor this out. And why is that? Well, because now we're looking for a null space. Right, so we have a set of homogeneous equations, right? When we have a matrix, and I mean, think of this as any other matrix, right? Just take the A minus lambda I and, do those operations. I have a matrix, call it M. Now I'm looking at the matrix M times the vector V equals the zero vector, which is just a null space, all right? So then finding the eigenvectors for an eigenvalue means that we're solving this homogeneous systems of equations. And when we did that and wrote the solution in vector form, we were getting a basis for the null space. And that's exactly what Margalit says right here, that if I have an n by n matrix A and lambda is an eigenvalue of A, then the eigenspace that corresponds to that eigenvalue is the solution of A minus that lambda, that eigenvalue, times the identity. And what is that when I solve this homogeneous system? Well, it's the null space of this matrix. There's something to remember about eigenvalues. They aren't specific, right? Eigenvectors. Eigenvalues are specific. But each eigenvalue has infinitely many eigenvectors. Why? Well, the whole point is that they're scalar multiples, right? So I can take any scalar multiple of an eigenvector, and it will also be an eigenvector. And so it's important to know that the eigenvalues are distinct. They're unique. There's just one for each of those eigenvalue-eigenvector pairs, but for the eigenvectors, there can be lots of them. Definitely you should look at these examples of how to compute the eigenspaces. And after you're done looking at the examples, you should definitely read through the updated invertible matrix theorem. So we've got a couple more things now that we know because we have learned about determinants now, and we know that a matrix is invertible whenever that matrix has a non-zero determinant. So as soon as I have a non-zero determinant, I know all of these things are true as well. And also, well, let me just say that I get a 0 as an eigenvalue of A when I get a 0 determinant. In other words, 0 is an eigenvalue of A when A is not invertible. And when A is in fact invertible, then 0 cannot be an eigenvalue for it. The same as the determinant can't be 0 for an invertible matrix, right? If the determinant is 0, I have a non-invertible matrix. So we have these two new things to add because of determinants and eigenvalues. So definitely take a look at all of the interactive examples and the geometry in this section, and we'll be back with more eigenvalue, eigenvector stuff. And it's going to get really cool really fast when we talk next time about the characteristic polynomial.